subject of this video is the reduction of various acid derivatives with lithium and aluminum hydride. And the products will be either alcohols or amines, depending on whether the acid derivative contains nitrogen or not. And we know that lithium aluminum hydride is a very reactive source of hydride that generally has to be done in ether or THF solvent. And the reaction is always followed by an aqueous acid workup. Which means that the products will in fact be alkoxide ions, not alcohols. The aqueous acid workup is what will protect the alcohol. So these are hydride sources of H-. But the aluminum hydrogen bond is covalent enough that the hydride can act as a Lewis base or a nucleophile rather than as a Bronsted-Lowry base as it would for simply lithium hydride. So even carboxylic acids like propanoic acid in this case can be reduced using lithium aluminum hydride in ether followed by aqueous acid to produce the primary alcohol, 1-propanol. Certainly there's an acidic hydrogen here, and in the presence of acidic hydrogen, the first thing that's going to happen is lithium aluminum hydride is going to deprotonate that with the liberation of hydrogen gas. And that's an irreversible reaction because hydrogen gas is pKa is 38, and pKa of your average carboxylic acid is somewhere on the order of 5. So this equilibrium, such as it were, would be approximately equal to 10 to the 33rd, which obviously goes to completion. And generates us lithium salt of propanoic acid, or lithium propanoate. If you had a less reactive hydride reducing agent than lithium hydride, that would be the end of it. The hydride reducing agent would simply convert the carboxylic acid into its salt, and you'd be done. But lithium aluminum hydride is so reactive that it can donate another hydride and create a dianion. So the first hydride acts as a base in the Bronsted-Lowry sense. The second hydride acts as a nucleophile or a Lewis base. And the product of that anion. But this anion can rapidly react to the alate that's generated in the process. That negative charge out. The precise mechanism of this reaction is not known with certainty, but the aluminum oxygen bond can be broken. And the resulting species, because it has a -2 charge, would be an even more powerful hydride reducing agent than lithium aluminum hydride. So it could very readily donate a second hydrogen. To generate the alkoxide. New trivalent oxygen species, and we've got a couple of lithium ions floating around. So this lithium alkoxide is the product of the first step, and then in step 2, aqueous acid will protonate to generate the product. And that equilibrium will lie strongly to the left, as the way I've written it here, to form the alcohol, because the pK of the alcohol hydrogen is 15, and hydronium ion is -1.75. Right? So that's an effectively irreversible acid-base reaction. So a very active, reactive hydride reducing agent. It's not possible to stop at the aldehyde stage, because the aldehyde, in fact, is more easily reduced than the carboxylate ion, since the aldehyde is not negatively charged. The carboxylate ion is significantly stabilizing positive on this carbon by proximity to the negatively charged oxygen. So it stands to reason that if lithium aluminum hydride is a good enough reagent that it can reduce the carboxylic acid itself, it should be able to react with any other carboxylate derivative and more readily, because the other carboxylic acid derivatives are not going to form that negatively charged carboxylate ion that slows down the reaction. So, for example, an ester we have methylpropanoate, would be expected to react with lithium aluminum hydride through a standard basic nucleophilic acyl substitution or acyl addition elimination, where we first have the hydride adding to the positively polarized carbonyl. Addition in step 1, and then in step 2, we're going to have the loss of the leaving group. To form the aldehyde. The aldehyde then is reduced again. By the standard mechanism that you are already familiar with from first semester, to generate the salt, it could also be bound to the aluminum, that's the alane. You can remember the stoichiometry of reduction of aldehyde to lithium aluminum hydride is 4 to 1, 4 aldehydes to 1 aluminum, since it's a source of 4 hydrides. And then we have the aqueous acid workup. Primary alcohol that we would have generated from reaction with carboxylic acid. So it's less steps in the mechanism because we don't have the negatively charged intermediate forming in the first place. standard, steps 1 and 2 here, standard nucleophilic acyl substitution. And then steps 3 and 4 here are standard nucleophilic acyl addition. So in this 4-step process, we have both of those two classes of reaction presented. Nucleophilic addition followed by loss of leaving group, and then nucleophilic attack followed by protonation to effectively add hydrogen across the carbon-oxygen double bond. It makes sense, I hope, that if this were an acid chloride, you would undergo exactly the same mechanism. The leaving group would be chloride instead, but apart from that, everything would be identical, and the same if it were an anhydride. The only difference would be a change in the identity of the leaving group. The ester is in fact less reactive than the aldehyde because we have participation of a minor resonance form that takes advantage of the load and bear on the methoxy group to stabilize the partial positive charge on carbon. So instead of just one additional resonance structure, 2 total, which we would have in the case of the aldehyde, we have this 3rd resonance structure, and that's the reason for the lower reactivity of the ester. Because the ester is less reactive than the aldehyde, it's not possible to stop at the aldehyde stage. The acid chloride, on the other hand, is more reactive than the aldehyde because the participation from the resonance structure with the double bond to chlorine is negligible, and that's because of the core orbital overlap between the chlorine 3p orbital and the oxygen 2p orbital. So, in theory, it should be possible to stop at the aldehyde stage in the reduction of acid chlorides if we can fine-tune the hydride reducing agent to be something that's reactive enough to react with more reactive acid chloride, but not reactive enough to react with the less reactive aldehyde. And there is such a reducing agent, and we'll talk about that in the next video, which will discuss the various ways of synthesizing aldehydes from acid derivatives. But for now, we want to consider what would happen for the other acid derivatives, the ones that contain nitrogen, if reduced with lithium aluminum hydride in ether or THF. I used ether before, I'll use THF this time just for the heck of it. And the product will be different. Product now will be propanamine or aminopropane. So it's 1 aminopropane. And it's a primary amine. From a primary amide, we're going to generate the primary amine. The amide is even less reactive because the contribution of the resonance structure with the double bond to nitrogen is larger than the contribution of the resonance structure with the double bond to oxygen in the case of the ester. But lithium aluminum hydride is such a good reducing agent that it's going to reduce it anyway. NH2 minus is a terrible leaving group. But we're in basic solution with hydride. So it can still leave in this particular case. And then the aldehyde is much more reactive than the ester, so we will get to the solution reaction. Oops, sorry. Messing up here. lose the oxygen, not the nitrogen. So in this particular case, because NH2 minus is a poor leaving group, we're going to take propionate generate the heavy aminal. And you know that the heavy aminal can be converted into the imine by propionation. Still on the wrong mechanism. Scratch that. My apologies. So the first step is, as I stated, the donation of the nucleophilic hydride to the electrophilic carbonyl group to form this alkoxide. That then reacts with the aluminum. And because of the presence of the nitrogen lone pair, this can be just as it did for the case of the carboxylic acid reduction. Generate an aluminium ion. The aluminium ion is now subject to further reduction, either by lithium aluminum hydride or by this even more reactive hydride reducing agent. Put that second hydrogen on there and generate the amine. So we've got a nucleophilic acyl addition reaction happening in the first step, first two steps. Where we have hydride donating to the carbonyl carbon, and then the Lewis acid, alane, ALH3, reacting with the oxygen. So we've effectively added the aluminum hydride across the carbon-oxygen double bond. Now we have the nitrogen lone pair taking out the leaving group. And then we have another nucleophilic acyl addition reaction to the aluminium ion. The aluminium ion, because it's positively charged, is obviously much more reactive than is the amide. stop, if you could stop at the aminium ion, then hydrolysis of the aminium ion would generate the aldehyde, and one could synthesize aldehydes from amides. It is in fact possible to synthesize aldehydes from amides, but not using lithium aluminum hydride. There's a different reagent that will accomplish that transformation. So the mechanism is a little different than the mechanism with the ester, and that's because the NH2- is a much worse leaving group that allows this reaction to occur with the oxygen rather than kicking out the NH2-. NH2- will act as a leaving group in hydrolysis of the amide by a strong base, aqueous base, but that wasn't the mechanism that I was supposed to be showing right now. Sorry, I got off on the wrong track. What about the reaction of nitriles? It turns out that nitriles, in this case, propane nitrile, will react with lithium aluminum hydride in ether or PHF, followed by aqueous acid, give the same primary amine in this case, and always a primary amine in the case of the nitrile, because there are no alkyl groups attached to that nitrogen, and there can be no alkyl groups attached to that nitrogen. Whereas if you had a secondary amide, you would reduce that to a secondary amine. So here, the lithium aluminum hydride donates to the positively polarized carbon of the nitrile through the standard nucleophilic attack, which is the first step of the reduction of all the acid derivatives except the carboxylic acid themselves, where we have that Bronsted-Lowry acid-base reaction to start. The negatively charged nitrogen can now react aluminum and we have effectively done a nucleophilic acyl addition reaction across the carbon-nitrogen triple bond, adding a nucleophilic hydride and then an electrophilic aldehyde. So directly analogous to the reaction with the amides, except that the nitrogen anion is now adding to the aluminum, the alane, the AlH3, rather than the oxygen anion. This is still a carbon-nitrogen double bond. It's still quite reactive. Thus, it's possible for the second addition to occur. Possible that that nitrogen could react with another AlH3, another mole of alane, but it's likely that this waits now until the aqueous acid workup. And that Lewis acid-base reaction was reversible, so if the AlH3 falls off, then the nitrogen can react readily with acid. It's also possible, since this is a negatively charged intermediate, we don't really want that in acid solution, it's possible that the nitrogen would get broken first, and then the Lewis acid would fall off. And that's perhaps more likely in acid solution. But either way, we're doing a nucleophilic acyl addition reaction, a second reduction, and then the acid workup is cleaving the aluminum off. Eventually, that aluminum will become aluminum hydroxide. And unfortunately, lithium aluminum hydride reductions often generate an insoluble precipitate of aluminum hydride, or aluminum hydroxide rather, AlOH3, which is insoluble in the aqueous solution, and sometimes gums up the reaction and makes it difficult to isolate the material. So the mechanism is slightly different for the reduction of the different acid derivatives, but the product is always an amine from either amides or nitriles, and a primary alcohol from acid chlorides and hydrides, carboxylic acids themselves, or the esters. We'll talk in the next video about attenuating the reactivity of the hydride reducing agent so that we can stop at the aldehyde stage instead of going all the way to the primary alcohol or the